share with you some of our recent work of the CO2 reduction. And for this work, I'm going to show you today the Rijie and Sherlock on the one doing all the theoretical calculations, and Jose Rodriguez that all the experimental application today. And to start, I want to briefly tell you about what we do at Brookhaven within the Catalysis program. So one of the things we do is really interested in CO2. As you heard from previous talks, that CO2 activation of CO2 has obvious benefit. I wouldn't spend more time on that. But specifically, what we're interested is really reduce the CO2 using either green hydrogen or the light outputs from the abundant greenhouse gases and shale gases. So one of the focus is really find a good catalyst which can increase the conversion of the CO2. But more importantly, what we're also interested in the selectivity, which in some sense is more important than conversion. And specifically, one of the things we focus is selective reduction of the outputs. And in addition, in some of the cases that is very difficult to achieve, then we're also interested in selective production of syngas and the alkanes, which can be further converted to the alcohols via the tandem by the hybridization reaction. So these are the reactions we're interested in. And the catalyst we're really looking at is we call it complex catalyst, where you involve a lot of ice at the interface. I will get back to this later and show you why we're interested in this. So to do that, we use the integrated approach. On one side, we're looking at the practical powder catalyst, which has more relations with the industrial catalyst. And we use different techniques, lab-based, synthesis-based, XRDs, XFs, and measurements, try to describe the structures and the behaviors using in situ and random measurements. However, due to the complexity of this catalyst, so the understanding is rather limited. And to do that, we also combine with the well-defined single crystal-based autocatalyst, which the purpose is try to mimic the behaviors of the powder catalyst, but in addition is allow the use of the surface science techniques like the STM, PMBIM, XPS, so that you can get more information about the surface structures, the species, and how it behave under reaction conditions, and that is relevant to the catalysis. And another benefit of using model catalyst is it can involve theoretical modeling in more meaningful ways. And for theory, it really can nail down to the molecular level, looking at what is active size and how the active size behave under reaction conditions. And this is very important for the development of catalyst. So back at Brookhaven, we're combining the in situ and random characterizations for powder catalyst, surface science studies, model catalyst, and theoretical studies, and trying to understand how the catalyst behaves. And from there, we want to extract design principles and guiding us to moving ahead how we can optimize the behaviors of the catalyst. So my research is really focused on the theory side by combining density functional theory and kinetic modeling, whether it's kinetic mechanical simulations, microkinetic modelings. We also combine with the machine learning methods, try to get understanding from the molecular levels. And that's will also be the focus of my talk today. So specifically, we did a lot of stuff, but I will give you one example in my talk today, showing how we do that for the CO2 hydrogenation to methanol, which is the theme of these sections. So you heard a lot from previous talk, but I just want to re-emphasize that if you're looking at the gas-phase reaction from CO2 hydrogen to the methanol, it's a slightly exothermic reactions. So that means the reaction is merely inhibited by the kinetics, and that's shows that the catalysis can be very important. Another thing that besides the CO2 to methanol, there's a side reaction which always been involved which is the reverse water gas shift reactions. And I will show you later that for copper-based catalyst, and this can be very competitive pathways, which can limit the conversion as well as activities. So then, as I said, catalyst is important, but if you're looking at literature as mentioned previously, that there is an industrial fact covers the incandescent oxides. And also, there are a lot of efforts trying to get the best catalyst, whether it's copper oxide catalyst, polysulfide based, polycarbide based, or the modified Fischer-Tropsch synthesis catalyst. So all these efforts are really targeting that the challenges we have right now for the CO2 hybridization to methanol catalyst, which suffers from relatively harsh conditions, relative high temperature, and extremely high pressures. And also the yield selectivity still is problematic. And also there are still a limited understanding of the reaction mechanism. So if you're looking at the literature, even for copper, pure copper, and different mechanism has been proposed. And here I just to show you a schematic of two major pathways, including the fomate pathway, where the CO2 hydrogenation first to fomate, followed by different intermediates, because it's been proposed differently depending on what kind of calculation you did, and eventually gets to formaldehyde and further hydrogenation to that. Or you can do reverse water gas shift pathway, forming the CO first and then followed by the CO hydrogenation to So our strategy is really trying to understand the mechanism of the catalyst and where the reaction takes place. And from there, we want to develop idea that how we can improve the yield and the selectivity. And based on that, we try to model the reaction conditions by lower the temperature or lower the pressures. So what we did here, now we start with the basic. So copper, which is the most highly active pure metal catalyst we have right now. So first thing we did, using the copper bond one as a base material. We did that, and also other groups has did that, the same thing. And what we find here using DFT and kinetic color simulations is that, well, there's only one type of active size on the surface, which is highly coordinated copper. And if you're looking at the potential energy diagram, then the coming from the fomate pathways and the production rate is pretty low due to the highly activated hydrogenation of rate and another thing we find that we said the reverse water gas shift is competitive, but for the pure copper, in this case, the reverse water gas shift pathway is more populated than the fomate pathway, and therefore it leads the CO as a major product rather than methanol. And that's actually agrees with our experiment that I have said with Rigas, where this is a Rigas plot looking at the CO2 hydrogenation from copper 101, and you see that the huge increase of the rate when you're really compared with the methanol synthesis and the reverse gas shift reactions lead to the COs. And now, question we ask ourselves, well, is there any way we can improve that? And to do that, we first just to find out what are the problems. And along the kinetic models, so what are the barriers to allow the CO2 conversion and specifically to the methanol? Now, what we did here is sensitivity analysis. So these are first order derivatives and really looking at the sensitive of each barriers involved in the kinetic model and to the CO2 conversion rate or the methanol selectivity. So to make the long story short, what we find that there's two things can be very important. First thing is the barrier for the diaxomethylene hydrogenation. So basically what we see here, if you can lower the barrier for diaxomethylene hydrogenation, you can improve the methanol selectivity and production rate. But however, that effort is not as significant as in changing the CO bindings. So here we specifically find that CO binding on the copper-based catalyst should be moderate. It should be strong enough to avoid the desorption of the CO. So therefore, you have more CO to do the methanol production. But the bindings cannot be too strong, which should be moderate enough to allow the CO hydrogenation further to the net. So having this kind of idea in mind, we try to find a way to do the optimization. So here our goal is really how we can promote the methanol selectivity from CO to hydrogenation. Well, we start point is the copper surfaces. And our strategy here is really try to increase the complexity of the catalyst in a way, in a two-dimensional way. One dimension is to bring some restructuring of the catalyst. So rather than have highly coordinated coppers, we can have different kind of copper sites on the surface. Another dimension is we try to increasing the type of the decorated promoters or modifiers on the surface. So specifically what we do here, on one way, we're going from the surfaces to the nanostructures. And if you're looking at the difference here, that going from the surface to nanostructure, and the surface can go not only one type cherries, but you can have another orientation of facets. On the side, you can have low coordinated stack and kick sites. And in addition to that, you also introduce a lot of surface strains when you're going from extended surface to nanostructures. And all these efforts can change the binding energy and therefore tune the activity of the copper. And another dimension, we are increasing the number of different type of functional sites on the surface. We're going from pure copper surface to the copper alloys by introducing the secondary metals. Or we can go into the metal oxide interface. Now we're increasing the type of active sites from 1 to 3. And here is the pure metallic copper, oxygen, and another secondary metal. So the hypothesis is really that because we can introduce in different type of active sites, and these type of active sites can provide different or select bindings to specific reacting intermediates. So therefore, that allows big tuning angles for changing the activity, well, and the selectivity. But whether that is the case, then we have to do further KT-based and kinetic modeling. And to make the long story short, what we find here that, as I mentioned in the previous slide, the CO binding for these systems are very. So what we find here that going from the surface to the proper nanostructures, you actually can increase the binding of CO, where the low coordinated copper really have to stabilize the CO, and that's also helped to the methanol activity. By going to the copper alloy, it also helps. Here is the CO binding. Here you see that when you're introducing palladium, platinum, nickel, and rhodium on the surface, you do see the significant increase of CO bindings, and therefore the methanol production rate, especially for nickel. And I see Eve in the audience, and he had to work years ago to really nicely show that the promotion effects of nickel doping on copper one with the CO2 hydrogenations. But of course, you cannot overdo it. Like rhodium, if you put it on the surface, you bond CO strongly, and therefore, rather than promote the reactions, you actually lead to the contaminations of the surface active sites. And you can also do that using the metal oxide interface again, and the interfacial sites, they are synergistic effect to stabilize the CO bindings. And of course, you lead to the increase of this methanol activity. But everything looks good, except that for all these systems we have been studying, none of them has be able to lead the methanol as the major product. CO still remain as the major product. So therefore, we ask ourselves, is there anything we can do to really have as the major product from the CO2 hydrogenation? One of the things we consider is using alkyl metals. So what we does here is that we doped naphthalene metals on the static interface. And why we think about that? If you're looking at the literature, the provoking effect of metals is not something new, but it's just a lot of it hasn't been well understood, and different proposed mechanism you can read from literature, like the work function on the transition metal surface and the steric effects which can affect the approaching of the intermediates to the surface, and also the electronic effects by donating one electron to the nearby active sites. So therefore, you modify the electronic structures and bindings. And also, they can introduce surface cycles and can affect the bindings for intermediates via the dipole-dipole interaction, and also the synergetic effects is also being proposed. So one of the things that why we don't understand that well is that the experimental way is very challenging to determine the structures when you do the alchemists. And that's making it very difficult for the theory to give three models to describe what is the promoting effect of the active metals. So one of the things we do in our group is that we're looking at the potassium decorative copper oxide CPUs supporting on copper bond one surface, which is known as 44 structure. So experimentally, what we do here, we deposit potassium under oxidizing conditions on the 44 structure, and we find that they can form a pseudomorphic layers of potassium up to the 0.2 monolayers, and they have a well-defined structure. If we're doing the state functional calculation, we find that the potassium refers to the chemisoft oxygen sites, which is at the center of the hexagonal carbon dioxide ring. And the theory simulated STM actually described the experimental STM pretty well. And besides that, the theory also finds that the doping of the potassium actually can introduce the polarization of the surface density. So you see the accumulation of the electrons of the surface. In addition, it also decreases the surface function. So with all these introduced new angles, how can that affect the catalysis? So one thing we do is just looking at the binding energies before we can predict energy catalysis. So just looking here, I just want to draw your attention that if you're only looking at the CO2 bindings, you can see that with the potassium deposition, the CO2 binding is kind of increased slightly. So the kind of hypothesis that can help to capture the CO2 and then promote the CO2 conversion. Another thing I want to draw your attention is the fomate. The fomate binding has been significantly increased. They could be a good sign that you kind of calculate the fomate pathways, but it could be a good sign that you are generating a new surface, which is make the cast increase and react. And also, we find that the CO binding, if you compare with the 44 and copper mono, you actually decrease. That doesn't seem a good sign because, as I mentioned before, for the copper-based catalyst, you need to sort of increase the CU binding, and that's we get the benefit for copper alloys, copper interfaces. So what can happen? Then we have to looking at the detailed reaction pathways, and here I just showed the fomate pathway. We also did that for the reverse Mordechai pathway as well. And this is on the potassium, copper oxide, copper one surface. First thing we find that the deposited potassium is not really blocked. It participates in the reaction directly, forming a strong anchors for the oxygen containing stations. Another thing we find that the methanol prefers to be formed via the fomate pathway, which is not new. We see that from the other copper-based system as well. But differently, this is not via the typical formaldehyde-based fomate pathway, but rather that they have been sort of a methane diol species, which directly leads to the formation of methanol. Another thing we find that the fomate hydrogenation to fomate acid seem to have a higher variance about everything. But these are all sort of preliminary understanding based on the DFT energetics. And then to do more understanding, we have to look at the kinetics. Again, we combine the DFT with the KMC study and the typical experimental conditions. And we develop KMC matrix. We try to formulate the DFT calculated structure. So one of the things we find that because the potassium degradation, you're actually being able to stabilize the copper oxide much better than the case without it. Because if you're only looking at molecular structure, under these conditions, the copper oxide will be easily reduced to the copper under reaction conditions. Another thing we find is that the active potassium mostly remain active during reactions and not much in reaction intermediates covered or stabilized or block these sites under reaction conditions. And more importantly, we can get back to our question we asked ourselves. So how does the selectivity look like? And here is the KMC simulated selectivity under different temperatures. And first thing is kind of surprising to us is that, well, CO has been a major product of a lot of copper-based catalysts, but in this case, the selectivity for CO is only treatment, nothing. And in addition, when you have the temperature higher than 460 Kelvin, you actually see that the methanol is a major product. Of course, when you're increasing the temperature, the formic acid can kick in as side product, but up to 600 Kelvin, the methanol remain as a major product. So that's kind of really answers our question. Well, with the potassium decorated copper catalyst, we are able to achieve that. That is, the methanol can be the major. And why is that? Well, because we theory in the end find out what is the promoting effect. So here I just show you the potential energy comparative between the formic pathways and the reverse Wurtz shift pathways. So first thing is that because the presence of the potassium on the surface, and you can see that the formic pathway is more more populated than the reverse Wurtz shift pathway. Another thing is that, well, you go with the reverse Wurtz shift pathway, but once you reach to the formic acid actually prefer to merge with the formic pathway. So therefore, the reverse Wurtz shift and formic pathway became the same. So rather than produce methanol and CO is only a very small amount. And finally, we find that CO binding, which we identify as an essential sort of descriptor for the methanol synthesis. In this case, it doesn't matter. I mean, for the potassium decorated surfaces, the CO binding is pretty big, but you still can get higher methanol selectivity. And that's because the potassium totally changed the reaction mechanism at active sites. And now we ask ourselves, so CO binding is not important. So what is important? And then we have to go back to sensitivity analysis and really looking through the kinetic model and see which is more sensitive to the CO2 conversion rate, also the methanol conversion rate, production rate. So here, selective means that you got to lower the barrier, and positive, you got to increase the barrier. So and what we find here, you compare the same stack, you find that if you want to get both the CO2 conversion increase and methanol selectivity increase, sometimes it's impossible because you see these opposite shifts of the energies. And in other cases, it's possible. And like the formaldehyde binding energies, methylene binding energies, but we find out they can be useful, but not very sensitive. So the most sensitive is really the bindings of the fomate and formic acid. So if you want to achieve both the higher CO2 conversion and methanol selectivity, so what you need is you suppress binding of fomate and increase binding of the formic acid. But how can you do that? I mean, both things are very close geometries and on the same size. So how can you do that? And actually, we find that, well, it is possible that you consider the active metal as the water, because we compare the binding natures of the two intermediates on the potassium sides, actually they are forming different mechanisms. For the open shell fomate, it's more ionic. It's really the potassium-mediated charge transfer from the copper bond 1 surface to the balsamics. So therefore, the binding features to the significant charge transfer as well as very strong metals. But on the other hand, if you don't have post-shell-forming acid, it's actually there the electrostatic interactions. So what we see here, the transfer is really tiny, and often the binding energy is roughly. So going forward, we kind of based on these understandings. So will there be any possibility that we can change the substrate from couple with one is potential electrolyte to rather like deficiency of electrons, which can hinder the charge transfer from the support to the fomate. So therefore, you can weaken the binding of the fomate. And then eventually, it can also populate the electron density around the potassium. So therefore, you can promote the electrostatic interaction with the formic acid. Well, that be the case, then we have to go back to our sort of roadmap. And here we consider one way that we're introducing metal oxide, which is really lean of electrons compared to the metal surface. And we find that if you're using the metal oxide as support, we can also introduce the copper nanostructures, but still keep the number of type of active sites: copper, alpha, oxygen, and another metal and so whether that will work. Then one of the system we're looking at is the zinc oxide supported copper nanoparticles and the system. Again, before doing any mechanistic study, we're looking at the binding energy. Here, I just want to mention that if you're looking at the CO2 bindings, well, there's a significant increase of CO2 bindings if you compare with the potassium core structure. So therefore, a higher CO2 expected. Another thing, yes, we do see the increase of formic acid bindings. So whether it can help for the molecular synthesis. To confirm that, we're looking at the reaction pathways on the copper CCM zinc oxide surface, and we also include the copper zinc oxide for. Then what we find here is that by introducing CCM at the interface, you can significantly stabilize the reactive intermediates and transition state along the fluid pathway, which is lead to the methanol synthesis. Another thing is that, well, if you're looking at the structures with the presence of the cesium, actually the cesium, copper, and zinc oxide triphase interface is the active sites, where it can provide different bindings than the copper zinc group. Specifically, it stabilizes the fermion group, which is strong enough to allow the decomposition fomate to fermion, but enough to allow the further hydrogenation to. And then to confirm that, we did the KMC study, as I mentioned before. After typical experimental conditions, what we find here that the cesium can introduce a full magnitude increase in methanol production as compared to the copper zinc alone. And it's actually agrees with experiments which is led by Jose Rodriguez, where we see the increase of the methanol productivity by 2 to 3 orders of magnitude. And beyond there, we also find, well, the fomate is kind of stabilized, but actually the direct participation of the cesium, not the function, the promotion effect is really beyond there. And because what we see here that at the triphase interface, the fermion pair can be aligned in a way that the CC bond coupling is pretty easy, and there's no huge barrier. But if you compare to the case without cesium, and because the two fermion are kind of along parallel to each other, and the CC bond coupling has overcome huge barriers. So therefore, that it can go in beyond C1 and get to the C2. And in fact, what we find here, once the CC coupling for the fermion occurred And the intermediates can go the further hydrogenation, CO bond breaking, and then followed by further hydrogenation all the way to the metal. And there's no experience on that. And if you're doing the KMC simulations, actually we find that you do see the production of the ethanol under these conditions. But unfortunately, it's not as active as the single production, which is four orders of magnitude lower, and that's actually traced with the experiments where they show the 2 to 3 order of magnitude. So to summarize, hopefully I show you that the way that we have been developing the strategies really increasing the complexity of the catalyst. We are both restructuring and introduce different type of promoters on the surface. And with that, we're actually being able to change the stability of catalyst under back conditions. And in addition, we can also changing the selective bindings, which you cannot imagine that you're doing only one type of active cell functional catalyst. And eventually we can formulate the catalytic activities and selectivities. And in this case, we are able to not only promote the CO2 conversion, but more making a lot of efforts to tuning the selectivity, going from the CO to the methanol, and eventually working towards to the end. So now from there, we ask ourselves whether this is enough, right? I mean, we can do step by step, we can expand it in these pictures, looking at more complexity and really extend it along these two pathways. But these kind of efforts kind of limited because you have to work on the base materials and doing the modification bit by bit. So now we are changing ourselves and ask ourselves whether we can do more. And right now we are kind of developing a framework which can do the catalytic mobilization for complex catalysis and CO2 hydrogenation in one of them. And to do that, we need to really bring the machine learning surrogate to our considerations. So one of the things we do right now, we're making efforts to have a regression model, really establish relationship between for example, the mechanistic synthesis rate as a function of the areas in the kinetic. For example, here, if the rate we express as a function of the first order variance, which is Berry itself, and we also including the second order, the normalized second order variance, which is expressed by the harmonic mean, and this is really trying to account the interaction between the relevant steps. So what we find here is that for molecular synthesis on copper-based catalyst, and using these sensors, we can estimate the importance score of the descriptors we generated based on the various, and we can quickly identify the very descriptors. And we find that these descriptors can be very effective, and using that can be really estimate the rates, or in this case, mathematical activity, and the accuracy is much higher than the typical first order derivatives methods using sensitivity analysis, degree of control. And more importantly, we can go in really beyond a mathematical model, which is typically do for the machine learning. We can do the analysis for the descriptions and trying to find out that what the role of each descriptor and how the descriptors has been interacting with each other to allow eventually the behaviors you observe from the experiments. And also based on that, we can really identify the promoters, what the promoter do to the specific step, and eventually the whole locality. So going beyond there, we are kind of expand our efforts from methanol synthesis to ethanol synthesis, as well to other CO2 reduction reactions, and going beyond to copper-based to other conveyance materials as well. And the goal is really trying to get a deep understanding of the catalyst, how catalysts behave, and eventually we're trying to really developing a new framework which can efficiently allow the rational design multifunctional catalyst for these reactions. So finally, I would like to thank my internal collaborators and postdoc students, the extra hard work, and also external collaborators and DOE and basic energy science for the financial supports. And especially I want to thank the computing resources from different from NERSC, from the Center for Functional Nanomaterials at the Brookhaven, and also from the Seabook at Storybrooke. It's really allow us to do simulations of a complex catalyst under reaction conditions, which is more meaningful for the simulations that provide more useful understandings to catalyst designs. And with that, I will thanks for your attention. Thank you. Share with you some of our